Hello, Stephen. Thank you very much for joining us. It's Dr. Stephen Wolfram. You got your PhD in physics at 20, which is quite remarkable. And so some interesting story around your kind of education and how you seem to be a step ahead all the time, but still managing to, pull up the rear as well. So it might be interesting to hear a bit about that. You gave us cellular automata, new kind of science. It looks like some kind of bottom-up approach as opposed to top-down. And it's a fascinating sort of new computational approach to doing science. Want to talk about Rule 30, and I'm sort of curious to know whether that prize is still on offer. I have no chance of gaining the prize myself, but I'm just curious about that. The New Physics Project, which seems to be a sort of philosophical kind of extension of what you were doing with cellular automata. So much to get through. I've got tons and tons of questions, but I mean, would it be okay to just tell us a bit about your background, how you got into physics in the first place, and how on earth you ended up getting a PhD at 20?
Yeah, well, let's see. Well, I grew up in England, still have that accent, so you can kind of tell that. I was, I guess, in the 1960s, when I was a young kid, I was always interested in the future, and the future was often about things like space, because that was kind of the exciting thing that was happening at that time. So I got into those kinds of things. Sort of the various spacecraft became my personal friends in the sense that I knew all about them and so on. But that kind of segued fairly quickly to, okay, if you were going to design things like this, how would you do that? And that turned into an interest in physics. So by the time I was probably 10, 11 years old, I was kind of reading lots of physics books and got one particular thing I got interested in when I was 12 years old was a physics book that about statistical physics that had this cover illustration that showed kind of a collection of molecules that were initially in a very ordered state, and then in the later kind of frames in the film strip had become kind of disordered and random. And the claim of this book was that was sort of what was going on in the second law of thermodynamics. And I think in retrospect, I realized that the thing that was really exciting to me about that was this was a case where instead of just being told what was true about physics, the book kind of claimed that from first principles, you could deduce something that was true about physics. Okay, it's only decades later that I realized that was kind of the thing that was most exciting to me about that. But that got me interested in, okay, well, can I, for example, simulate the behavior of these gas molecules? I had access at that time, this is 1973 or so, had access to this very antiquated computer that was a thing with 8 kilowords of ferrite core memory, giant thing the size of a desk, programmed with paper tape and so on. And it's actually I was thinking maybe I even had a paper tape right here from those days. But in any case, I got interested in realized I could try and use this computer to do things like simulate these gas molecules and so on. Meanwhile, the big thing that was happening in sort of science at the time was particle physics was kind of in a very golden age, because quantum field theory looked like it was actually going to work. And there were a bunch of surprising experimental discoveries made, particularly in 1974. Being a then 14-year-old kid, I thought, well, I've learned a certain amount about physics. People are very surprised by these discoveries. I should be able to figure out something about them. And so I sort of set about doing that and published my first paper when I was probably, I guess it came out when I was 15 or so. It wasn't a very good paper. They got better. And they particularly got better when I kind of started using computers to do the kinds of calculations that needed to be done for particularly sort of algebraic mathematical calculations that needed to be done for the sort of working out the current theories of particle physics. I was always very surprised that other people didn't use that kind of methodology, but they didn't. And so, well, let's see, I went to, for British audiences, it's perhaps of interest. I went to Eton. I had a scholarship kid at Eton, and I learned Latin and Greek and all those kinds of things. And on the side, I spent my time kind of studying physics and wrote up a bunch of pretty elaborate kinds of summaries of physics and so on, which I didn't show to anybody for 30 years after that. But
Right.
that's because in the end they were sort of mostly done kind of book length things that I suppose were mostly done for my own purposes. I suppose that's been a theme of many projects I've done, that in the end I'm the primary audience that I really care about for these projects. You know, the other people are kind of a side effect as far as I'm concerned, so to speak. But in any case, so I left school when I was 16, briefly worked at a government lab in England, went to Rutherford Lab, and then doing particle physics stuff, and then briefly went as an undergraduate in Oxford, and kind of was at that point sort of writing lots of papers about particle physics and then also cosmology, which I got interested in. I guess I was very early to the idea of kind of connecting particle physics and cosmology, which became much more popular in later years. And then kind of well, ended up going to graduate school after a year or so at Caltech, and then sort of I could have gotten my PhD while I was still a teenager, but at the time I didn't really think of that being as something cool to be able to say one did. But as it was, then sort of interestingly, I had this kind of plan from when I was probably 10, 11 years old that I wanted to sort of be a physicist. And so, you know, age 20, I kind of was a physicist. And then I kind of, right after I got my PhD, I was kind of like, okay, what am I going to, you know, what's the big plan, so to speak? And by that point, I'd become kind of the world's largest user of kind of algebraic computation systems,
Right.
and which I used to sort of do kind of what might have seemed to people like sort of magic calculations in physics, where people kind of would assume that I was some, you know, calculating whiz, which I was completely not. Me with my computer was pretty good. Me on my own, pretty useless. The, uh, it And so I had, you know, sort of maxed out what had been built so far in that area, and kind of couple of weeks after I finished my PhD, I was kind of started into the project of building a big computer system to kind of be able to extend sort of the kinds of things that I thought I could do with kind of computational tools. And as in doing that, kind of my idea was sort of think about all the computations one might want to do and kind of figure out what are the primitives by which you can do those computations. It's kind of like the natural science approach to computation of, you know, what are
So
the
reductionism is like the reductionist approach with the mathematics themselves. What are the basic units that can be built up into those forms, right?
Right. So I ended up coming up with this idea that sort of was kind of my version of what had been done in mathematical logic in the early part of the 20th century, of what amounts to representing everything as a symbolic expression. So everything has this kind of standardized form in terms of these kind of symbolic constructs, and then that the main operations have to do with transformations on symbolic expressions. So I started building the system that was based on that. It was a system called SMP, Symbolic Manipulation Program, and that was my first really big software system. Was kind of finished in 1981, and that kind of backed me into starting my first company as well. It was a system that had a lot of interesting ideas, I think, about sort of how you structure computation so that sort of people can understand it and it can powerfully be done. Anyway, I kind of, after that, I sort of got back into basic science, and I had long been interested in the question of kind of how does complexity arise in nature and the universe and so on. And I kind of thought, oh, you know, you're trying to figure out the shapes of snowflakes, things like this, you know, how you get this sort of randomness in turbulent flow. I thought, I know all this stuff from quantum field theory and mathematical physics. This should be easy. You know, let me just kind of crush these questions with all these mathematical tools I know. So I tried to do that for a little bit, and it didn't work at all.
Mm,
So then I was like, okay, well, what's the alternative? What else could one do? And it was very convenient that I'd had this experience in sort of understanding the foundations of computation from a very practical point of view in building my SMP system. And so that kind of got me into this question of, well, what if we just use computation as a basis for thinking about what happens in nature? How might that work?
mm,
And that then got me into the question of, well, what do simple programs typically do? Most programs that we care about are ones that we write for some very specific purpose that we have in mind.
mm,
But if we just make sort of enumerate possible very simple programs, what, what do these programs typically do? And so it was a very simple experiment to do. And that got me started on what I later found out other people had called cellular automata, though I was looking at kind of just these simple one-dimensional lines of black and white cells or whatever with
mm.
little rules that say kind of what should happen on the next line going down the page.
Yeah.
And the big surprise was that even though these rules were really simple, the patterns that I got out looked really complicated.
Mm,
Now, somewhat embarrassingly, in retrospect, I kind of was particularly concerned with what happens when you start with random configurations of black and white cells. How does that kind of form something more orderly? And
mm,
how does it form something orderly but complicated? But I had already generated pictures that showed what happened if you start from just, let's say, one black cell, everything else is
mm,
white. What happens? You get these kind of triangles. Sometimes you get kind of fractal type patterns. Sometimes you get other things.
mm.
And I hadn't really paid that much attention beyond the ones where I could explain what was going on, because I kind of had the intuition if the rule was simple, the initial condition was simple, somehow the thing you get out must be correspondingly simple.
Mm.
And that was, for a year or two, that was kind of what I thought was the case. And I had studied all these examples of sort of complicated behavior with more complicated initial
Mm.
conditions. And I always kind of had this idea that somehow the complexity you got out was already somehow hiding in the thing that you had
Yeah.
started off with.
Mm.
And then actually just about exactly 40 years ago now, I sort of was looking, well, I just got a laser printer, high resolution, computer printer, and I thought, just as a test of this thing, let me print out a nice big image of Rule 30, which
Mm.
is one of these very simple computational rules. I print it out, and it's like, wait a minute, this is really complicated. What's going on
Mm.
here? And then I realized I'd actually published little pictures of this in papers from 2 years earlier.
Without noticing it.
Yeah, without really paying attention to it, without really
Yeah.
internalizing what was going on.
Mm.
And I kind of realized that yes, there was something, a really big phenomenon here that sort of in the computational universe, even though the rules may be simple, the behavior will not be.
Mm.
And in retrospect, another thing that happened at that time, by that point I was working at the Institute for Advanced Study in Princeton, um, and where there lots of talented people, particularly mathematicians, and a bunch of very good mathematicians had gotten interested in the stuff I was doing and like, we're going to figure out how these cellular automata work.
Mm.
So they sort of wheeled in the methodology that they had for doing that, and they completely failed.
Right.
They they found nothing,
So,
and they were
Stephen, just briefly, if I may
yeah.
ask, so some of the simpler rules and the emergent shapes that they produce, are they deducible? Can you deduce those initial conditions from the emerging pattern with those ones?
Yeah, I mean,
Right.
what happens is some of them produce repetitive behavior. Like they'll
Mm.
make kind of a checkerboard, drafts board, pattern.
Mm.
Then some of them will uh, will make a nested pattern where you just have kind of triangles nested within triangles, but in a very regular way. Although intricate, it's still very regular.
Mm.
So those are cases. I mean, the thing really to concentrate on is, given that you know the rule and you know how it starts off,
Mm.
can you immediately say what's going to happen after a billion steps?
Mm.
If the answer is yes, then you've got something which is kind of computationally reducible, where you can kind of, where you can sort of, where you can feel much smarter than it. You've kind of crushed it. You can say everything you want to say about it. The, the thing that is the big surprise with something like Rule 30 is the pattern is is very complicated. You can't immediately imagine a way to say what will happen after a billion steps. And in fact, the belief is that it's computationally irreducible, in the sense that the only way you can work out what will happen after 1 billion steps is just run it for 1 billion steps and
Mm.
see what happens.
Yeah.
And there'll be little tiny, tiny patches where you can make statements about what will happen sort of more efficiently than just running it. But mostly you just have to run it to see what happens. And
Mm.
you mentioned the Rule 30 prize, which is something that I sort of put up there in 2019 because even after all these years, there's an incredible amount we don't know about Rule 30.
Yeah.
Even some very elementary kinds of things, which I think are sort of, there's always the question when you sort of define a prize for things, there's the question of in which century will the prize be won?
Yeah.
And you
Factor in
know,
inflation and stuff, yeah.
yeah, right,
Yeah.
right. It's what and for example, I was very lucky in 2007. I had kind of made a guess about what the very simplest possible universal Turing machine might be.
Mm.
And I put up this prize, I don't know, $25,000 or something for can somebody either prove or disprove that this Turing machine is universal? And I had no idea whether this prize would, be something that somebody, I mean, I knew nobody was going to give me an answer in a month
Mm.
because we knew it was much harder than that.
Yeah.
But I didn't know this would be out there you know, for 100 years or for 1 year or but as it turned out in that particular case, this young chap in England in about 4 or 5, 6 months came back and said, yep, I've got a proof. It was a very complicated proof. It
Mm.
took a while to kind of go through it and get reasonable confidence that it was really correct. A bunch of it was sort of very computational, so that was easy to
Mm.
verify. Um, but
Is
so
he
that
on
was
the team now? Is he on the team now?
unfortunately not. He turned out to be a very uh, not a very he interacts, I think, mostly with very abstract things,
Mm.
and is kind of a I would say is yeah, we actually we hope to recruit him, I'm not sure what he's doing right now. I try and check in with him every so often, but
Mm.
I think he's unfortunately you know bits are his friends. I'm not sure that humans are.
Mm.
Um, the um, the uh, I think the thing that so that was a really good experience in sort of putting up a prize for something,
Mm.
and it was a very well-defined question. And in the case of the Rule 30 prize, I've sort of broken into several pieces. So one of them is you make this pattern of Rule 30, and the you can ask the question, if you look at the center of this pattern, what can you say about it? And it's a very simple rule. Started off from just one
Just
black
a
cell.
single strip down the middle.
Yeah,
Right.
just a strip in the middle.
Mm.
And so far as one can tell, that sequence of bits is completely random.
Right.
Now, when I say completely random, it's kind of like the digits of pi. There is a way to generate the digits of pi
Mm.
that you can just say it's the digits of pi. But once you've got those digits, there's so far as everybody knows, there's no sort of regularity to those digits
Mm.
other than just saying they're the digits of pi.
Yeah.
And
Yeah.
it seems to be the same thing with Rule 30. But
Mm.
so one of the questions in the Rule 30 prizes is, does that center column ever become periodic? The
Right.
answer, I would be absolutely amazed if it did,
Mm.
but we don't actually have a proof that it doesn't.
Mm.
And so, and even computational irreducibility doesn't tell us immediately that it doesn't. It just
Mm.
tells us that in general, you won't be able to predict what will happen.
Yeah.
Any specific question, you might be able to kind of bite off, so to speak, even though the whole thing is still out there.
Mm.
So, but so it's we get people sort of sending us little pieces of progress on Rule 30, but I would say that I can't really predict. It's like I'm often have this situation with technology that I can readily tell this is going to happen, but I can't tell when.
As a matter of interest, Stephen, what would that change anything in your thinking about cellular automata and Rule 30 if someone does come up with a solution? I mean, would that change the way you think about it?
Um, it would make me feel even more confident,
Mm.
depending on, I think the things that are sort of part of that prize are things that are kind of more pieces of evidence for general principles. So, for example, the proof of the universality of this very simple Turing machine is a piece of evidence for this principle of computational equivalence that I think is a sort of very big and important principle. Basically, just says if you make computational systems, even when their rules are quite simple, above some very low threshold, the computations that these systems can do will be equivalent in their sophistication. So it's not the case. You might think, oh, I build a fancier computer, it will be able to do a fundamentally fancier collection of computations. The principle of computational equivalence says that isn't true. It says that instead, once you're above, once you get beyond just things that do periodic stuff and nested stuff and a few other things like that, you're in a situation where basically every system you can create does computations that are sort of equivalent in their sophistication. And that principle has a lot of consequences. For example, it's the reason for this computational irreducibility phenomenon, because if you say, I've got this system, it's doing what it does, but I'm going to be much smarter than that system. I'm going to predict what that system is going to do. Well, you are effectively also doing a computation, and your claim has to be that the computation you can do is somehow going to outrun the computation that the system itself is going to do. But the possibility of outrunning is kind of a story of I'm going to be able to do more sophisticated computations than the system, but the principle of computational equivalence says that isn't true. There'll be equivalent computations of equivalent sophistication between your brain or your mathematics or your computer or whatever and this little system you're trying to study. And that's the reason that there's computational irreducibility. And so so anyway, this principle of computational equivalence is a very sort of broad principle for which we're not going to be, we can get more and more pieces of evidence that this is what's going on. And, we can kind of home in on it in a variety of different ways.
When you say what's going on, do you mean in the real world? I mean, do you think that may I ask if you have any sort of metaphysical inclinations about the true nature of reality? And is reality computational in and of itself, do you suspect?
I think so. I mean, I think I wouldn't have said that with such confidence until 4 years ago. But I think at this point it all seems to fit together. I mean, the whole, there's really a big story that that kind of in which it's sort of a slightly long story, but the kind of the tip off was this kind of fundamental theory of physics that we developed in 2019, 2020 was something that I had kind of been, so once you've seen cellular automata, you kind of know that even when there are simple rules, there can be very complicated behavior. And so the ultimate question that you might then ask is, well, what about the whole universe? Could the whole universe be something which has simple rules, but all the rich, complicated behavior that we see?
Yeah.
And I knew very quickly that cellular automata weren't going to make it. They were not going to be a way to represent space and time and things like this in a faithful fashion. I learned only fairly recently that interesting thing about the history of these things. So, back in antiquity, people were arguing, some people said the world is discrete, it's made of atoms. Some people said, no, it's continuous, everything flows in some way. And that was kind of a debate that continued for a couple of millennia. And then
Democritus,
finally,
I think, yeah.
What's that?
Democritus was one of the first, wasn't he? He was an atomist, wasn't he?
Democritus was an atoms guy, and Heraclitus was a flow guy, and
what was Pythagoras? No, hang on. What was the there's the paradox, isn't there? Zeno's paradox.
Yes.
The infinite divisibility of space means you can't get from A to B, essentially, and stuff like that. So would that have been continuous? That's a continuous view of it, though.
That's a continuous story. Yes.
Yeah. Okay. Sorry. Yeah. Just that's interesting. Yeah.
No, I mean,
it's interesting they go all that way back to antiquity. Then we still haven't quite, solved it yet.
Right. But so what happened is you could make the same. So a lot of what was being discussed there was about matter. Sort of distinguishing space from matter was something that only sort of vaguely was that was the concept that space was a thing, as opposed to just you can put Cartesian coordinates in space. People just thought of space as being the background.
Yeah.
But then by the end of the 19th century, it was becoming clear that matter was made of atoms, that matter was not continuous. And then very soon thereafter, it became clear you could think of light as being made of discrete photons. At that time, and this I did not know until recently, basically every serious physicist assumed that space would turn out to be discrete.
Yeah.
And
Einstein did, didn't he? Yeah.
yes,
He thought, yeah.
Einstein did,
Mm,
or Heisenberg, all these people
mm,
thought that space would be discrete. And it turns out the model they tried to make was essentially something like a cellular automaton,
right.
where you have discrete cells, kind of like in a crystal.
Mm,
And they never published anything about it because they quickly saw that it wasn't consistent with relativity. And so it's confusing in the history of these things because there aren't papers that got written
mm,
saying space is discrete like this. It was just that's what these people believed. And by basically the end of the 1920s, beginning of the 1930s, they'd sort of given up and they'd said, like Heisenberg, for example, had sort of tried to make a discrete model of space, it completely failed, ended up with this thing he called the S matrix, where he said, I'm just not going to talk about what happens inside the mechanism of some physical process. I'm just going to say, what's the transformation from the initial states to the final states?
mm.
And that's what I'm going to talk about. And I'm going to try and work out properties of the so-called S matrix, that is the mapping from initial states to final states, and try and ignore what's happening in the middle because I'm so confused about things like discrete space.
It's a
So,
black box. Yeah. Yeah.
right. So then so discrete space kind of disappeared from the story, and several generations of physicists kind of grew up with the assumption that space is continuous.
Mm,
And so one of the things that's sort of a very, continuous space, continuous things aren't very consistent with how we think about computation. Computers, Turing machines, all those kinds of things are discrete. And, in the 1980s, for example, physicists just thought physics isn't computational. It's physics is continuous. Physics involves differential equations, things like this. Computers are discrete and involve these kind of discrete steps, and they're a different kind of thing.
mm,
And and I guess I was probably responsible for really pushing the idea that no, one can think of physical processes as computational. At the time, I wasn't so much thinking of physics all the way down. I was thinking of, oh, you can describe a fluid as making molecules, which you can think of as having very simple discrete characteristics, et cetera, et cetera, et cetera. Or you can use discrete models of physics, not that physics was sort of discrete all the way down.
mm.
But I kind of wondered maybe there might be a way to do this. And by the beginning of the 90s, I'd sort of started thinking about the idea of kind of networks to represent the structure of space. So in a cellular automaton, you have kind of like in a crystal, you have a rigid grid of cells laid out in space. So what I started thinking about was, well, maybe space consists of discrete points that are just connected in some network
Mm.
without having a precise definition of sort of where every point is. It's just,
But
well, we
just
know,
just briefly, can I briefly ask? So is matter a property of space?
yes, I think
Right.
so.
Okay. Okay. Thank you.
I mean, which is something very bizarre. I mean, Einstein
Mm,
had wondered that. Einstein was thinking maybe there would be some, black hole-like configuration of things that could represent something like matter.
mm,
I was reminded recently, when I was probably 14, 15 years old, I went to some talk by some well-known physicist in Oxford, I think. And we were talking about black holes, which were kind of still a very hypothetical thing at that time. And I was like, excuse me, but could particles like electrons be black holes, be little tiny black holes? It's like, oh no, couldn't possibly be, doesn't, just doesn't work that way. You don't understand what's going on, more or less. It is amusing to me that it's looking to me very likely that actually that's what's going on. And
really?
that, uh,
Wow. Okay.
so, which is kind of sort of a statement that something like an electron is a feature of space. A black
Mm,
hole is purely a feature of space. I mean,
mm,
the thing about black holes is they're made from stars collapsing,
mm,
usually, but once they're made, all that really matters about them is the sort of configuration of space-time that's
Mm,
associated with them. The thing that's crushed inside, you can't see, and it doesn't really matter.
mm,
So it's and it's that's that my current guess is, so it's, in a sense, a black hole is just a feature of space.
yeah.
And and so I think that's true also of material particles. I mean, that's a longer story, but I actually made some progress on it in the last few weeks. And I think maybe have a uh, um, maybe it's simpler than I thought it was.
I
Um,
think I think that one of the most exciting things I've heard about from the science project, the physics project, is the idea that you're getting close to unifying things like sort of relativity with quantum field theory, and so I mean that's just
yeah,
that would be
yes,
absolutely
yeah, it's it's very
flabbergasting.
cool. It's
Yeah,
very
it's
beautiful.
extremely cool. Yeah, and
Right.
so
I mean,
what's the latest on that, Stephen? And where are we with that?
well, I mean, you know, I think I know how things work. I think that, going from sort of having the intuition and having the basic structure to filling in, dotting all the I's, crossing all the T's, that's a lot of work.
Mm,
And the things that will really kind of nail that are having experimental predictions. We have kind of the prototypes of those predictions, and having somebody go and turn their telescope in the right direction
mm,
and see something totally bizarre that, we expected and that was completely unexpected in any other way.
yeah.
And I am confident that will happen. I cannot tell you the time frame. And
Mm,
it's one of these things where, like technology prediction, it's kind of like you can see that things will inexorably happen, but knowing is it this decade or is it 3 decades from now is very hard, because there are a
mm,
lot of different factors that come into play. And I think, but in terms of how well, so the first thing is, okay, it turns out one can have a model of kind of the underlying structure of space, and in the end, the only thing in the universe is space. And there's this giant graph, hypergraph, that represents the structure of space and everything in space.
mhm,
So it's kind of like, if you have a fluid like water, there's a bunch of molecules there, but there are things like eddies in the water that you can say, well, that's a definite eddy and it moves through the water.
mm.
Just like, but nevertheless, it's not,
It's still
there's
water.
not,
Yeah,
yeah,
yeah.
it's just water.
Mm,
And it's the
mm.
same kind of thing with matter in space, that, a thing like an electron is, I think, just a feature of the structure of space.
So it's a persisting form or a persisting eddy within that spatial
Yes, yes.
manifold, should we say? Right. Okay.
Right. Well, it's
Okay.
not a manifold. That's,
Oh, it's not
would
right.
that it
Okay.
were a manifold, because manifolds are, I mean, a manifold is kind of a mathematical construct that has the feature that it's sort of a continuous thing. And if you look under a finer microscope, what you find is Euclidean space. You find
Right.
space that has things, points that are arbitrarily close together, just the way Euclid said that space should be made. I mean, in Euclid, the very first common notion is a point is that which has no part. In other words, points are indivisibly, infinitesimal, so to
Mm.
speak.
Yeah.
And that's, in the kind of the arc of the history of science, I think in the end, the very first common notion of Euclid is wrong. And one can think of
Mm.
sort of the idea of curved space as being sort of the realizing that the fifth postulate of Euclid, that two parallel lines
Yeah.
will never cross, that
Mm.
wasn't right. But actually, it's even more basic. The
Mm.
very, very first thing that Euclid said isn't really right for physical space. And so the thing that one's starting with this kind of sort of everything in the universe is made of this hypergraph. The hypergraph represents the structure of space and everything in it, so matter and everything like that.
Mm.
Time is something very different from space. Time is the kind of progressive rewriting of this hypergraph. Time is kind of the inexorable doing of computation. Now, that's different from what one might think of from relativity, for example, where, I think Einstein never really particularly thought that time and space were the same. They were just related. Minkowski had this realization that there was this nice kind of mathematical form in which you could kind of package space and time together. And so really, really promoted this idea of space-time as a sort of elegant mathematical construct. But in our models, time is fundamentally very different from space. It's fundamentally this progression of computation. The fact that space and time are related in the way that relativity says is something you have to derive. It's something
Right.
that is not obviously true. I mean, it's, there are many things like this. If you have, I don't know, if you have a piece of graph paper, you've got squares on the graph paper, and you make a random walk where you just start from a particular point on the graph paper and you randomly follow one of the edges of those squares. You keep doing this for a while, you'll make this pattern that is circularly symmetric. Even though there are squares on this piece of paper, the emergent thing you get looks like a circle that doesn't
Right.
notice that it was on a square grid. And it's the
Right.
same kind of thing with the
So,
emergence
so you've got a
of
sort of discrete foundation that gives the appearance of the continuousness that as things
yes,
are right. Okay.
and also the relationship between space and time that one expects from relativity is something that, again, sort of emerges as a large-scale phenomenon, but it isn't the underlying thing about what time is. It's very different from space.
Mhm.
So, so the story ends up being, well, in fluid dynamics, for example, you've got all these molecules bouncing around, and sort of the big fact about that is that all those microscopic collisions and so on, on a large scale, they give you the equations of fluid mechanics.
Mm.
I mean, the mathematical I dotting T crossing of that derivation has been 100 years. We've been waiting for that for 100 years. I think actually some things I've done fairly recently about thermodynamics get us closer to being able to do that in a fully rigorous way. But it's a complicated story. But in any
Mm.
case, the operational fact is that the limit of all those molecules bouncing around are the equations of fluid mechanics. So
Mm.
similarly for this hypergraph and its rewritings and so on, the limit of all those microscopic processes turns out to be the equations of space-time, the Einstein equations. So that's
Wow.
kind of that's, I knew that actually in the 1990s.
Mm.
And I thought that was pretty interesting. And it was kind of funny because at the time, because I'd done physics and, well, not only had I done physics, but also the tool I built, Mathematica, was pretty
Mm.
universally used by physicists. It's kind of I had many friends who are physicists, and in the 1990s, they were all like, "String theory is going to solve everything.
Right. Mm.
We're on track. We're on final approach for the final theory type thing." And when I would tell them about, oh, there's this network thing that gives general relativity, they would kind of like, oh, I don't know what that means. It's very alien. Um, so
So
I
Stephen, just briefly, I'd heard that people doing relativistic physics actually use your software to actually validate some of their so it's actually being used as a validation tool for relativistic
well,
physics, which is a massive pat on the back,
right.
isn't it?
So there are two different branches here. I mean, our
Right.
Mathematica system is pretty universally used for
Yeah.
traditional
Yeah.
relativity kinds of studies. The
Yeah.
the the new stuff from the physics project, yes, it's pretty cool that, when you do relativity theory, when you do general relativity, gravitation theory, and so on, using the Einstein equations are continuous differential equations.
Mm.
But on a computer, it doesn't deal with continuous differential equations. It deals with some discretized version of that. So what you actually have to do is make some discrete approximation. And
Yeah.
what's traditionally been done is go from the Einstein equations to the discrete approximation and hope that you didn't make a mistake in doing that discrete approximation. What
Mm.
happens with our models is you start from this underlying discrete structure, which you know from sort of a mathematical development limits to the Einstein equations, and then you sort of make a big version of that and use that to approximate what happens in actual space-time, and that
Mm.
seems to work nicely.
Mm.
What's kind of interesting about that is if one finds a deviation from what the traditional Einstein equations imply, then people who are using this as a method for solving the Einstein equations might be upset.
Mm.
But for us, it's super great
The
because
discovery,
it
yeah.
means that there's a place where one can actually potentially see the effect. One can kind of have the space-time microscope, so to speak, to see down to the microscopic structure of space, beyond what one gets from this existing continuum theory, so to speak.
Mm.
So it's kind of, and one of the things that I'm I'm really curious about is what are the effects that are residual effects, even at a large scale, of the fact that things are discrete at a very small scale.
Mm.
So a great example of this, I think, from the history of science is heat. People wondered for a long time, what is heat? And they said, well, it flows from one thing to another. It must be something like a fluid they called it caloric fluid. And it turns out that's not what heat is at all. Heat is the microscopic motion of molecules associated, but you only could imagine that if you know that matter is made of discrete molecules.
Yeah.
Wouldn't make any sense without that.
Mm.
So the question is, now that you imagine that space is made of has a discrete structure, what is the kind of space-time analog of heat? What are the consequences of kind of all those microscopic details of what's going on?
Mm.
Well, I have a guess, which we'll see whether it's right or not. My guess is that dark matter is at least deeply related to this phenomenon of space-time heat. So in other
Right.
words, and that would be, in the history of science, it would be kind of one of those sort of typical arcs of what happens, which is, at the time when people were wondering what is heat, they said, well, the only thing we know about is fluids, so it must be a fluid.
Yeah.
And for dark matter, the only thing we know about right now is particles, so
So it
it
must be
must be made of
particles.
particles.
Mm.
And it's kind of ironic, perhaps, that it could very well be that its very name is already off track.
Right.
That is, that it's not matter at
Because
all.
it's not matter. It's part of space, a configuration of space of some sort.
Yeah, exactly. So that's an example of something we're
Mm.
hoping in the next not too long we'll be able to kind of home in on understanding by simulations and other things how that might work. I mean, it's kind of
Right.
would be a lovely irony also because Brownian motion, which was the thing that really clinched the idea of the existence of molecules,
Mm.
was Brownian motion was discovered in the 1830s, but it wasn't interpreted until around 1900. So
Right.
it was, and that was the thing where, well, but people were lucky with molecules. Molecules are big enough that they kick little pollen grains around, and you can see that under a
Mm.
microscope.
Yeah.
Whether we'll be lucky with the elementary length, whether that is big enough that we'll be able to, in you know, in the next few decades, measure it is not clear. What
Mm.
is nice about it is there are many different effects. There are many different things from both structure of space-time and quantum mechanics, which all depend on the same parameter. In our
Right.
model, there's basically only one parameter, which you can think of as the elementary length, the elementary time. It also has another characteristic, which I can explain, which is what we call the maximum entanglement speed. So but put that aside for a second. The main point is there's just one parameter. We don't know how big it is. It may be the elementary length is around 10 to
Mm.
the minus 100 meters, which is very small. And the question is there any effect which is sort of sensitive, which probes things at that smaller scale? Now, something like heat, you don't have to know about, you don't have to be able to pick up a molecule to be able to sense the effects of heat.
Mm.
And that's so the question is what things
What is
are
the
there like
equivalent?
that?
Yeah. Mm.
But so in the case of in this general arc of sort of how physics works, there's kind of the story of space-time, then there's the story of quantum mechanics, and the what happens in our models is there's this hypergraph and it has these rules for how it gets rewritten, and the thing is those rules do not define a unique path of rewriting. That is the rules can be applied in different ways. And so you end up with these different paths of history. And that is what sort of inexorably gives one quantum mechanics. And the
Mm.
thing that is, to me, when I realized this, it's like really quite a wow. It's the following thing. So in space-time, the big story is Einstein's equations. Einstein's equations connect the presence of energy, momentum, mass, whatever, to the curvature of space-time. So they are defining, and the curvature of space-time says, if you want to go on the shortest path from here to there, what will that path be? If space-time is flat, that path will be a straight line. If space-time is curved, that path will curve. And so the phenomenon of gravity is a consequence of the fact that mass, energy affect the curvature of space-time. The curvature of space-time determines the paths that particles and things take. Then those paths get deflected by the presence of mass, and that's how that works. So in our models, what happens is energy turns out to be, and again, I was quite surprised at how simple this is, turns out to be associated with essentially the density of updating activity in the
Right.
network. And then what happens is that density of updating activity affects the kind of these shortest paths and produces the Einstein equations, which give you gravity and so on.
So that
So that's the story in
density,
space-time.
so is that to do with, is that information? Is that the amount of sort of transformational changes that are going on with a given system?
Well, I don't know. I think, I mean, come on, think about it that way. I mean, it has to do with what, you have the state of the system, and you're asking, you're saying, well, yes, you change the system to another state. I guess one could say, I mean, can one think of it as a rate of I think it's a bit of a slippery concept, but I think the I suppose you could, it is in a sense a rate of processing of the state of the system and how it changes.
Mm,
It's kind of how much change is happening in the system.
mm,
Um, I'm here's why I'm hesitating. The problem is that what one means by quotes information is quite slippery. That is to say, this is, um, you could say, well, how much information is there really in the universe? Well, for example, in Rule 30, I can just tell you it's Rule 30, it starts from one black cell. Then I generate this giant thing. And the question is there more information in that giant thing than there was in me telling you it's Rule 30 and it has that simple initial condition? Or in the case of pi, I can say it's pi. But then when you actually get the digits generated, it's sort of an infinite sequence of things that seem random to you unless you know that it's pi.
mm,
And so there's sort of a whole question about when people talk about, information theory and things like this, what they're usually thinking about implicitly is something where the way that you can sort of grind down the signal that you get is very limited. You're saying, oh, I'm just going to break it into blocks and I'm going to use some kind of code that is sort of a very simple, well-defined code. And
mm.
that's kind of what gets meant operationally by amount of information, but it's not, in some sense, the real amount of information. So it gets
Mm.
kind of tangled. I mean, the thing that
This reminds me of your thoughts on observer, the observer problem. There's a dotted line from here to that, isn't there? I think, and that's
yes, there is.
that
Yes, there
absolutely
is.
fascinated me because that's kind of one of the biggest challenges of science in a way, isn't it? To somehow sort of peer around the headset, as Donald Hoffman would sort of put it, to somehow bridge that gap. And it sounds like you're onto something with this. Would you be
Well,
able to
I think,
talk
I
us
mean,
through that?
okay, so the main issue is, uh, in the end, what matters to us about our experience of the world is what our kind of internal perception of what's going on is. And, you know, there may be lots of atoms jumping around and there may be lots of pixels on the screen, but we only notice certain coarse features of that. And turns out the laws of physics that we have critically depend on that fact.
Mm,
So the most obvious example of this is the second law of thermodynamics, law of entropy increase, the thing that kind of was one of my first sort of big interests I was mentioning before in physics, of kind of how do things go from being very regular to seeming very random,
mm,
even though at a microscopic level, the laws of physics are reversible. So if you knew the position of every molecule, you could just reverse the movie strip and get back to where you started from.
mm,
But that's not our experience of the world. And so that's a case where the way we are as observers critically affects our experience of the world. If we were observers who readily could work out all the details of how all these molecules are interacting, we would just say, well, there's just a bunch of molecules that are interacting in some way. We wouldn't say,
mm,
oh, the second law of thermodynamics is happening, and we go from this very regular initial state to this random heat. We'd just be saying the molecules are doing this or that thing. But it's because we are observers who have this kind of computational boundedness that we just have to say, when we're confronted with a system that has, well, for example, computational irreducibility, we just have to say, we don't know what's going on. It looks kind of random to us. And so we build our experience of the world and our laws of physics on the basis of the way that we are as observers. And so the way that this gets sort of really, as far as I'm concerned, sort of super interesting. Actually, there are two more steps worth saying, because otherwise it's kind of hard to understand what's going on. So we're talking about quantum mechanics. I was talking about how, you know, there are many different paths of history that you can produce. And the way to sort of think about things is the universe has these different paths of history which branch and merge and so on. And just like we are observers of a gas, for example, on a large scale compared to molecules, so we are also observers of the universe on a large scale compared to all these microscopic paths of history. So a kind of a weird thing is that our minds, like the rest of the universe, are branching and merging and so on. So sort of the story of what has to happen in quantum mechanics is a story of how does a branching brain perceive a branching universe. And one of the things that happens is this kind of, you can think about all these different branches of history, and they're all related to each other. So two branches of history we can think of as very close together if they share a common ancestor, if they both came from the same previous state and then through, let's say, one recent branch. And so you can kind of map out all these paths of history in what we call branchial space, the space of quantum branches. And that branchial space is not physical space. It's not space where we move things around in the ordinary way. It's a different kind of abstract space. But it turns out there are laws of motion in branchial space as there are in physical space. And essentially what happens is, we don't know all the details of this, but the qualitative story is the presence of activity in branchial space is associated with energy, as the presence of activity in physical space is associated with energy. And in the end, that presence of that energy causes a deflection of paths in branchial space. And it turns out that deflection of paths gives one the path integral of quantum mechanics. So the kind of the super cool thing is that what is the Einstein equations in physical space, in branchial space is the Feynman path integral. So in other words, the origin of gravity and of quantum mechanics, it's the same underlying conceptual origin. And by the way, you can, when we're talking about these this hypergraph and the rewriting of the hypergraph that makes the things we observe in physical space, the branching of that rewriting that makes the things we see in quantum mechanics, those are all sort of integrated into this thing we call the multi-way causal graph, which is this whole thing that is sort of that one projection of it is physical space, another projection of it is branchial space and quantum mechanics. So it ends up that general relativity and quantum mechanics are simply different projections of the same object. And the underlying equations, the underlying sort of facts in those areas are the same thing underneath.
Right.
And even more kind of what's interesting is that, to me, is that both what we observe in physical space, what we observe in branchial space, those are sort of the interplay between us as computationally bounded observers and this underlying computationally irreducible detail of what's happening underneath. It's that interplay that leads us to believe in continuum space, to believe in quantum mechanics. It also is what leads us to believe in statistical mechanics and the second law of thermodynamics. So in a sense, all three of these big theories of 20th century physics, they're all at some level the same conceptual thing. They're all the relationship between computational irreducibility and our characteristic as computationally bounded observers.
So are you saying that physics is as much about our minds as it is about any external domain?
Yeah, I mean,
is it more about us than it is?
Well, okay, so the even bigger picture here is when we talk about, well, we got this rule and it terms the rewriting of this hypergraph, the next question you would ask is, well, why did our universe get this rule and not another one? I was very confused about that for quite a while, until I realized that actually one can think of it as being that all possible rules are being run. And you get this thing we call the Ruliad, which is this sort of entangled limit of all possible computational processes. And so it's a bit of a, it's a difficult conceptual thing, because the Ruliad is this entangled limit of all possible computational processes. We must be part of it.
Is
So
the
the
Ruliad the
question of,
concept? Is it the conceptual equivalent of the laws of physics? Is that
not really,
no? Okay,
it's more, it is a thing that is a matter of pure necessity. Once you have the definition of computation, the Ruliad must exist and
right.
is unique. It is just the, the Ruliad is, well, actually things which are in the end probably equivalent to the Ruliad have arisen as kind of limits of abstraction in mathematics and other kinds of things. So it's
Okay.
an object which everybody, including me, was surprised that nobody had ever looked at this object. Nobody had ever really conceptualized this thing. And it is, in the end, it's a sort of obvious thing to look at. But in any case, the kind of there's this thing that we are necessarily part of. And so you have this difficult question of, what does an observer embedded within this Ruliad conclude about what's going on in the Ruliad?
Hmm.
And the answer is, what they conclude about it depends on what they're like. So if you looked at all possible observers, you could conclude sort of all possible things about what's going on. But the thing is that there's a sort of contingent fact, which is we are observers of the kind we are. So we're observers who, for example, believe that we experience a single thread of time. We have, that's an example of something that we believe about the world. And another thing that can be said about us is we're computationally bounded. Our minds are finite. And so we don't get to sample the whole Ruliad. We only get to sort of look at some tiny piece of it. So then the big surprise, the thing that really I very much didn't see coming in terms of the philosophy of science, is it becomes the case that given the Ruliad, which is a necessary object, you can't get away from its existence. It isn't a thing where you could say, well, maybe there isn't a Ruliad because it's an abstract thing. And it is a necessary object. Okay,
Yeah,
given
just
that,
just briefly. So just let me get my head around that. So in order for there to be different perspectives on physics, there has to be something for which there can be different perspectives on. Is that the
well, but
claim
it's
in
more
some?
than
Is
that.
that right? Okay.
It's more than that. It's given that you have defined the idea of numbers and defined operations on numbers, 2 + 2 = 4. You can't get away from it. You can't say, oh, if I have rocks that are red instead of green, 2 + 2 won't be equal to 4. Once you have sort of the definition of terms, it necessarily is that way. And so it is with the Ruliad. Once you have the
Right.
definition of the idea of computation, then the Ruliad necessarily follows. So then the question is, well, if you're an entity embedded within the Ruliad, what do you perceive about it? And then the answer is, well, it depends on what you're like. And so then, given that we are the way we are, the big fact is we necessarily perceive the laws of physics to be the way that we perceive the laws of physics. If we were not as we are, if we were not computationally bounded, if we allowed branching in our perception of time, if we had other characteristics which I can't really imagine, then our conclusion about the Ruliad would be different. So in other words, we would have different laws of physics. So our laws of physics are the interaction between the necessary features of the Ruliad and the sort of contingent facts about how we are. Now, for example, if you could say, well, our view of the universe is based on the fact that we're hanging out on this planet in this galaxy at this time in the history of the universe. If we were on a different planet, our view of what happens in the universe would be different. The things we care about will be different. If we were right close to the big black hole in the center of our galaxy, we'd probably have a lot of different things that we really care about, a lot of different things that we observe. If we were, many details of us affect how we perceive the world. For example, if the fact that we believe in space is a consequence of kind of things about our scale in the universe. If we were really big, if we extended halfway across the universe, we probably wouldn't think it worthwhile to talk about the expanse of space.
Yeah, journeys would be a bit less relevant to us, wouldn't they? Yeah, yeah.
Yes, if we were at a scale of the atoms of space, the sort of microscopic points, again, we wouldn't necessarily think it worthwhile to talk about this kind of expanses of space. And even, as I look around, I'm in a room here where I can see maybe 10 meters away from me. And, light comes to 10 meters away from me in a microsecond. So, but my brain takes milliseconds to process what I saw. So as far as I'm concerned, when I look around, there is a state of space that I'm seeing because the lights come to me, but I didn't know anything changed until my brain has had milliseconds to respond to that.
Yeah.
So we think about the world in terms of this space at an instant in time. But if we had brains that processed 1 million times faster, as digital electronics does, we would not necessarily believe in space in that same way. So there are lots of ways in which kind of our, and by the way, things like the fact that we perceive the universe from the vantage point that we do because of the planet that we're on, there isn't really a theory of why we're on this planet. It's kind of like, well, we just happen to be here, and that's where we are. You can't say, I have a theory that proves we're going to be on this planet rather than on another planet. That isn't a type of thing for which one has sort of a deductive scientific theory. So so there's an analog of that in the Ruliad. The question of where we are in the Ruliad is again one of these sort of contingent things. We happen to be at this place in the Ruliad. The way I like to think about it is every mind is at a different point in the Ruliad. Minds that are easy to communicate between are nearby in the Ruliad. Minds that are very different are far away in the Ruliad and may perceive a very different set of things about, for example, their physics. So
can I briefly just ask on this? Sorry, Stephen. Do you think there's anything unminded in the cosmos?
Well, the principle of computational equivalence kind of tells one that that sort of everything is a very wide range of things are capable of the same level of computational sophistication. Now, that means the weather really does have a mind of its own. The question is, how aligned is that mind with a human mind? And we have a very definite view of what it's like to have a mind. That we have this single thread of experience, we remember history, things like this. The weather, in the sense of being computationally as sophisticated as us, we can say it has a mind, but it doesn't have a human-like mind. So it's a question of how big a zone in Rulial space do you count as being mind-like? So we humans, we populate, just as we populate one particular planet, we populate a very small region of Rulial space. We can get, I've tried to do some experiments to understand, sort of how small is our region of Rulial space. It's really, really tiny. We have a very aligned view of kind of how to describe what's happening in the world. We're very, very close together in Rulial space. And so that's kind of a if so, the question of whether you consider something mind-like, if you say it has to be human mind-like, then you're saying it has to be in that small zone of Rulial space. To say if mind-like, if it's enough to be computationally as sophisticated as a mind, then that's all over the Ruliad. Now, it's like if you're interested in extraterrestrial intelligence or something, that's asking, you're interested in intelligence that is at a different place in physical space. But there's also the question of where is it in Rulial space?
Yeah.
And, our ability to sort of recognize and be aligned with intelligence, just as it's pretty hard to communicate across, large regions of physical space. So
Mm,
it's pretty hard to communicate across
mm.
Rulial space. I mean, we can kind of think, the cats and dogs are not that far away in Rulial space, and we have certain commonality with them. But, you go further away in Rulial space, and it's very hard to
Even
communicate.
identify them. Yeah, yeah. Even yeah.
Yeah, right, right. I
Mm.
mean, because it's kind of the, so I think,
Sure. So we were talking about the Ruliad. Did you want to sort of unpack that? The significance of it and what it really
well,
means.
I think we were particularly talking about kind of how the laws of physics that we have kind of emerge as a consequence of kind of the way that we are. So it's not the case that we're saying everything about the world is just sort of in our minds and based on us. There is a there, and it's the Ruliad, so to speak. But our particular perception of what's going on depends on sort of how we're sampling things in the Ruliad. And
Mm.
so it's sort of a funny slice in between kind of a philosophical point of view that sort of everything that's relevant is what's happening in our minds, and the point of view that there's sort of an objective reality that is independent of us. There is an objective reality that's independent of us, but it's big and complicated. And the thing that we consider our sort of internal reality, the thing that observers like us conclude as reality, is this kind of slice that we take because we are the way that we are.
Mm.
And
Mm.
I think that's some, that's kind of and there are a lot of kinds of things that point of view starts giving you answers to, like questions like, well, one question is, okay, what's the significance of consciousness in all of this? Consciousness is some complicated, slippery word, but I think operationally, there are features of sort of operational definitions of consciousness that have to do with, well, we actually aggregate everything into the single thread of experience. We're not, you might have thought that consciousness was kind of the top of some hierarchy of what systems are capable of, but actually, I think that's not the case. I think consciousness, in many ways, is a specialization. It's like we're only considering this perception of the Ruliad that is this single thread of history. And so, for example, you
Mm.
get things like, well, what, as time goes on and our species goes out and explores more stuff, we go and send spacecraft out, we expand in physical space. We also expand in Rulial space, in the sense that as we understand more points of view about the universe, just like we get more points of view by sending a spacecraft to Neptune or something, so we get more points of view about the universe by expanding our kind of conceptual, by expanding in Rulial space, in effect. And
Right,
so
right.
one of the things that you might ask is, okay, well, what's the ultimate future of history, so to speak? We might, colonize the universe. We might also colonize Rulial space. But
Right.
you might ask, well, what happens if we've extended our domain, our mind, so to speak, to all of Rulial space? Well, it's kind of a somewhat be careful what you wish for type of situation, because in some sense, if you expand to be everything, then you don't coherently exist anymore, in
Mm.
the following sense, that our sort of coherent existence relies on the fact that we are a specific thread of experience.
Mm.
As soon as we say, well, we're kind of expanding to everything, then there's no us there, so to speak.
Identity. There's no your identity just dissolves
Right,
into it. Yeah, yeah.
right.
This
So,
reminds me of something, Stephen. I just wondered if you could comment on this. So, it may have even been you that spoke about this on one of your many talks. But I've heard about these rats that can do mazes, right? And they're able to show that the rats can do arithmetic, right? Because they're able to understand to get out of the maze, they have to do every even door or every third door. So they've demonstrated the rats understand arithmetic. But then when they do prime number solutions to the maze, they can't get it. So it shows that it's possible to have a grip on mathematics that is constrained. And it just reminds me of what you're saying, that the idea of there being different kind of perspectives on the Ruliad would give
yeah.
us different physics. Is there
Well,
some
color me
logic?
suspicious about these animal experiments. They're always very hard. And it's kind of like, occasionally I've done things like, watch the videos of actual experiments that purport to show that, polar bears are not as smart as rats or something.
Right.
And it's very muddy. I mean,
Okay.
it's very muddy for an interesting reason, which is minds that are human-like, we understand. You
Mm.
know, we we even believe they exist. For example, I mean, all I know about you is a bunch of pixels I see on a screen, right? But I imagine that you have an inner experience because I know that I have an inner experience and you seem enough like me, so to speak, that I can kind of extrapolate that you have an inner experience.
Mm.
But your average polar bear may not seem enough like me that I can readily do that extrapolation. So it
Mm.
becomes really difficult. I mean, when you say, even between humans with very different cultural backgrounds and so on, it can be very confusing. Is this concept really a thing that human has? What
Mm.
does it even mean that the human has formed that concept? I mean, this gets one into sort of AI, neuroscience kinds of questions, like what is, how, when I think about a polar bear, that there is some pattern of neuron firings in my brain that represents that concept.
Mm.
But it's very hard to kind of encapsulate that. The only way that there is a sort of clear encapsulation is when I say the word polar bear, I've kind of packaged up that pattern of neural activity into this communicable lump of concept that is a word. And I think it's actually a funny thing because when you're dealing with motion in physical space, what is motion? Motion is for something to move, the thing has to stay the same thing. In other words, it's not obvious. It's something you have to actually establish in a physical theory that a thing can undergo pure motion. It can move without change. Now, in fact, it never is really without change because as it moves, it's made of different atoms of space. But to an observer like us, it can be like, oh, it looks the same as it did before. It must be the same thing, right?
Mm.
So now the question is, well, physical space, the things that move without change are things like particles, like electrons, or things like black holes. But the question is in Rulial space, what thing moves without change in Rulial space? And I think the answer is it's basically concepts. In other words, to get from one mind to another without change, there is a packaged concept like a polar bear, like the concept of a polar bear that moves without change in a sense from one
Mm.
mind to another. And it's then unpacked at the other mind, and its instantiation in that other mind will be very different. It'll be a different pattern of nerve firings and so on. So it's but this question of what, did the other person form the same concept of a polar bear, so to speak? That's a hard thing to say because their pattern of neuron firings will not be the same.
Mm. Yeah.
So to say it's the same is a kind of an observer-dependent thing. You say it's the same. Why do you say it's the same? Well, it's the same because when they talk about a polar bear, they say similar things to the things the first person said when they talked about a polar bear. So it must be the same kind of thing inside. It's an observer-dependent observation. Now,
Yeah.
in when we ask about, for example, AIs, we can ask the same question. Do they, when we say, well, is the AI conscious, let's say, well, does it have an inner sense that we can project our inner sense into? And or does it have can we identify where is that concept inside the AI? It turns out it's very difficult to do that. The same reason it's difficult in brains. It's, people have said for years, oh, you do this fMRI, you see this region of the brain that lights up for your particular brain when you have when you're thinking about polar bears. And so the question is, how does that really work? I mean, do you, if you take a large language model, for example, is there a particular region of its, a few million neurons, hundreds of billions of connections, and so on? Is there a particular region that kind of lights up when it thinks about polar bear, when it's about to? Well, ultimately, the answer is it's going to have the tokens that correspond to polar bear, and they're going to light up by the time it's writing out polar bear. But what happens upstream from that inside the system is much less clear. And in fact, the thing I'm just working on right now has to do with the foundations of machine learning and trying to understand when a machine learning system learns, what is the thing that's happening? So in other words, it could be the case. We're used to machinery where we can understand how the machinery works. We're used to sort of mechanical machinery where there's a cog and another cog and a lever and so on, and we can kind of see the things move. Now, what's not obvious is that when a machine learning system, or a brain for that matter, learns something, is there a sort of mechanical narrative explanation that you can give for what's going on? So I did a project recently, which I had started in the mid-1980s, but through wrong intuition did not finish at that time, which had to do with biological evolution. So the question in biological evolution is, why does it work? How can we get from how do we manage to get all the kind of things that biological evolution discovers? So I have this very simple model, actually happens to be based on cellular automata. You have the cellular automata and it has, 50 rules, let's say, that just specify what happens with particular patterns of bits. And then the evolution consists in randomly mutating elements of those rules. Okay. And let's say you want to make a pattern that starts from a single cell, lives as long as possible, and then dies out. So you keep mutating that genome, the rule, and most mutations, the thing will just go splat, or it will kind of, be tumor-like and just grow forever. So there's every so often you'll make a mutation, and the mutation will cause it to, for example, live longer. So you ask, well, what is it? What actually happens? And what you find is there are two very surprising things. One is that it can successfully find mutations that will let it live longer. And two, when you look at what it does when it lives longer, you don't understand what it's doing. So in other words, what you see and the progression of living longer, patterns, you see it sort of had an idea. It was able to make a triangle of this kind. Then it builds on that idea and it makes 3 triangles of that kind. Then it does something else. What you see in these sort of sequences look very much like what the fossil record looks like. That is, there was an idea, something invented legs, and then it elaborated the idea of legs and it got feet and other things and so on. And, you see this kind of progressive elaboration happening all the time, but and there are different paths depending on what random numbers you happen to pick. You will get a different path of evolution with different outcomes. Different, the creature will look different, so to speak. And you can even trace out in the simple models that I have. You can actually trace the complete tree of life. You can trace all possible mutations that could have happened, and you can see that there's a branch on one side that's based on one idea, a branch on the other side that's based on another idea. It's kind of like the reptiles break away from fishes or something.
So biology has its own branchial space in some sense.
Yes,
Right.
biology has a branchial space, and it's very beautifully analogous. The thing I just described is a multi-way graph, just like the one that leads to quantum mechanics. And the kind of at any given moment in biological history, paleontological history or something, we are looking at a slice of branchial space, and we're looking at sort of the ancestral relationships between organisms in the tree of life are essentially related to branchial distance.
Wow.
So it's kind of neat, and you can see essentially event horizons forming where you've got sort of these separated parts of the tree of life that won't interact again, and so on. So
Right.
it's rather lovely. But the point I was going to make there is that one of the surprising things is that the way the thing manages to, for example, live a long time is incomprehensible. That is, you can trace the bits and you can see, yes, it works, but you would never have come up with that from an engineering point of view.
Yeah.
Now, the second big surprise is that it can find those solutions. And that's actually a consequence of computational irreducibility that has to do with kind of the space of possible directions it can go and the effective randomness in that space and the fact that you don't get stuck. but that's a separate phenomenon. The most relevant phenomenon
Mm.
here
Mm.
is the phenomenon that you end up with kind of behavior that achieves an objective, but in an incomprehensible way. In other
Right.
words, when you look at it, it looks like it just happens to work. It's
Mm.
not like it, you could have told it would work. It just happens to work. Well, I think the same thing happens in machine learning. That is, I
Right.
think that when a neural net, for example, learns something, it uh, it it just happens to work. It is not that it has a structure that has a narrative explanation to it. It's that it made this complicated structure, and you're kind of probing the right part of this computationally irreducible space to, you're identifying this is the thing that I'm going to pick out. And by the way, it's the part that allows me to talk about polar bears.
Sort
Um,
of heuristic, or is it kind of thing?
well, I don't know. It's a thing where it's it's more like there's sort of an encyclopedia of all possible encyclopedias, and the thing that corresponds to human knowledge are these things that corresponds to useful knowledge. We just happen to find the piece of the encyclopedia. And it's
Mm.
the encyclopedia sort of already exists. It's kind of like the Ruliad. It's already out there, but we're just
Mm.
sampling a piece of it. And that's the part that we're so in a sense in machine learning, what it seems like is that we are picking out these pieces of this very complicated thing that we can use as the kind of struts and trusses and things to make our structure of knowledge that we're interested in. So
Right.
it's not, so when you say, well, how do those trusses actually work? The answer is it's incomprehensible because it just happens to work. You can,
Mm.
it's just like in the history of technology, for example, people, use donkeys for a long time. Donkeys do what donkeys do, but if you ask the question, how does a donkey work? It's complicated
Mm.
and not relevant to the use of a donkey for the sake of moving your wheel to operate your mill or something.
Mm.
It's so I think that's the story. And so when you say, is there a certain thing in there that you can identify? Yes, I can see the mechanistic operation of this thing, of the rat that's figuring out this or that. I just don't think that's going to work. I think that it is a story of, well, within any computationally irreducible system, there are always patches of computational pockets of computational reducibility. So there will be some things you can say. They
Mm.
may or may not be things that are exciting to you. That is, you
Mm.
might be able to say about some, oh, I don't know, some thing in molecules bouncing around. You might be able to say, well, there'll be this particular little configuration of rings of molecules that happen. And you might say, well, that's amusing, but I don't really care. What I care about is only some feature of the kind of large scale flow of the fluid or something.
Mm.
And so these pockets of reducibility, like in Rule 30, there are pockets of reducibility. There's a certain amount of regularity on one side of the pattern, or there are these little white triangles that form that last for a certain amount of time.
Yeah.
And that those are things you can talk about in a reducible way. Um,
Mm.
and the question for something like neuroscience is, are the pieces that can be talked about in a reducible way the pieces that we think are interesting?
Mm.
Or are they things, and I mean, I think, yeah, so I mean, there's this sort of question of, well, for example, whenever we talk about natural laws, a natural law is essentially an effort to go from nature as it is to something that we can understand in our minds. That's kind of, in a sense, what a natural law is. It's taking some aspect of nature and having a narrative explanation of that that fits in our finite minds.
So something like causality, for example.
Yes, that will be an example of a feature of the world that is a sort of a simplified explanatory feature. But I'm thinking more about I don't know, something like like laws of fluid mechanics, where
Right.
there are lots of underlying molecules bouncing around, but the only thing we care about is the overall velocity moves
Mm.
in this way.
Yeah.
Um,
Mm.
and I think that um, so those are so we can be, when we find those pieces of reducibility, we're, that's what finding natural laws is about. Those pieces of reducibility must exist, but they might or might not be ones we care about. So what does it mean, care about? Well, for example, one thing is, well, we can use it for technology. Another thing is the sensors that we happen to have notice those kinds of things.
Mm.
I mean, we could have very elaborate, fluid pressure sensors that notice all kinds of features of fluids.
Mm.
Maybe dolphins do, I don't know,
Mm.
that sense all kinds of things like that. And so knowing all kinds of little correlations about pressure sensing, pressures in fluids might be highly relevant to us. They're not particularly relevant given the sort of sampling that we're doing of things.
Can I just briefly ask on that? Is there a sense in which the Ruliad gives us a chance to speculate about other types of minds and other? Because I think you hinted at something earlier. You said that if we can gain conceptual insight,
Yeah,
and
I mean,
and I just wondered what form that would take, and what that actually looks like.
well, I'd love to have a way to think about how other minds think about things. That would be I am always an enthusiast of sort of diverse points of view, and I've been trying to get out of the actual mind that one's stuck with.
Mm,
It would be nice to be able to imagine another point of view and not
yeah.
imagine the view of the world from another mind.
Yeah, I mean,
There's some
Wittgenstein talks about these language games, doesn't he? And how we talk ourselves into a particular understanding of the world, but actually, even just from an ordinary human understanding, we could change that. We could radically alter that as well.
Yeah, well, I mean, there are pieces to that story that have to do with things like whether a concept can really be translated from one human language to another, or whether in the end, language is this kind of shared social construct that
Mm,
allows one to transfer, concepts from brain to brain and things like this.
mm.
And, in the end, it's a mere approximation to what's actually happening inside, so to speak. And I think that
Chomsky seems to think there's a universal grammar, doesn't he? So I think the sort of semantic or perhaps syntactic structure is the same for all of us, irrespective of the aesthetic look and feel of the language. He's saying that
I don't
that's
know.
universal. I
I
don't.
haven't
Would
taught
you agree with that?
I haven't talked to Chomsky for a few years. The last time I did, he was uh, I think he was surprised by the concept of computational irreducibility, because my challenge to him was, you're interested in making a science of linguistics. Why do you think any such science is possible?
Mm.
And I think the uh, I don't know in any detail his views, and I think they've changed over time. But one of the questions is, for example, with large language models, um, one of the things I think we learn from the success of large language models is kind of a surprise about language, which is there's more regularity in it than we thought. And I think, people have known forever that there's syntactic grammar of language. English goes noun, verb, noun, typically.
Mm.
But there are many noun, verb, noun sentences that don't make sense,
Mm.
right? And so the question is, does the construction kit extend to kind of saying what sentences you can put together that make sense?
Mm.
So Aristotle started talking about this, um, but didn't get very far. And it's been kind of a lost question. And the LLMs have
Mm.
kind of shown us that, yes, there is such a construction kit, just as they can put together sentences or arguments that are logical because they can say, there's a pattern. It goes boom, boom, boom like this, just like syllogistic logic from the Middle Ages or whatever. Sentences have to work this way, so to
Mm.
speak.
Mm.
So similarly, I think they are finding kind of a sort of a construction kit for meaning. And in fact, I have a project I've been wanting to do for several decades, but finally actually am now doing that, aided by LLMs, is kind of trying to really make a sort of full symbolic discourse language, a full way of taking the things we talk about and turning them into a sort of abstract computational language. I mean, a lot of my life work basically has to do with taking kind of practical things in the world and making a computational language to represent those things.
So
Kind
would it
of
be a bit like propositional logic, but with a bit extra added in, or something like that?
I think propositional logic is a microscopic piece of the story. I mean,
Mm.
that was, that was as far as Aristotle got, basically.
Yeah, yeah. But
And
that's
that
the
was,
start of that journey, though. That's yeah.
yes, right. And people immediately start thinking, well, logic, it's the way of putting things together. Everything must be logic. That's just not right. That was what Whitehead and Russell thought about mathematics.
Mm,
Everything
mm.
can be constructed from logic. It was a big mess. I think I learned recently, actually, of a funny thing about the origin of neural nets. So neural nets, sort of in their very modern form, actually, kind of start off with this paper by Warren McCulloch and Walter Pitts in 1943, long time ago. And it's kind of shocking to
Perceptron.
me
Mm.
in the in the things I've been doing recently. I've been doing just a bunch of study of the foundations of machine learning and so on. And there are a lot of things you might ask about neural nets where I'm like, I just can't believe nobody has asked this in the last 80 years. And it's actually, well, at least with the technological tools we have, with our Wolfram language tools and so on, it's pretty easy to ask these things. But kind of my sort of thing I learned recently was back in the 1920s, particles were all the rage. There were electrons, there were photons, there were these kinds of things. Warren McCulloch had the idea that there might be psychons, as he called them, which were
Right.
elements of thought. And so he had the idea that maybe in the brain, what's happening is there are these elements of thought that are somehow interacting according to the laws of propositional logic. It's an interesting idea.
Mm,
It's
mm.
that segued in the end into sort of the calculus of the nervous system. I mean, it's funny, people have said things like that, like Ada Lovelace, actually, back in 1840, has a very nice quote where she says uh, she wants to work on the calculus of the nervous system, and she wants to bequeath to future generations her calculus of the nervous system, which sadly she died soon after that and didn't get to work out whatever it was that she imagined she was going to work out. But it's kind of people have been kind of circling around this idea of, is there a calculus of the nervous system, so to speak?
Mm.
And that was, at that time, calculus was hot. And so that was sort of the obvious thing to think about. I don't know to what extent that was kind of a notion that was in the air at that time. I mean, I don't think much so. So I think that was an
Mm.
Ada special, so to speak.
Yeah.
But I think uh, these questions about sort of other minds and how you think in terms of other minds. One example of that we have that's kind of nice right now is generative AI systems that are producing images. A piece of text that's not quite right is typically incomprehensible to us.
Mm.
Just a word jumble is just like incomprehensible. An image that's just random pixels is also incomprehensible to us.
Mm.
But an image that's kind of got clumps of pixels and things like that, we look at it and we get some idea we might be able to understand this.
Mm.
And so one thing you can
Mm.
do is look at a generative AI system, and you kind of have all of these vectors of numbers that represent kind of the thing it's supposed to be generating an image of, for example.
Mm.
When
Yeah.
it's, the notion of a cat, the concept of a cat is turned into some, vector of 1,000 numbers, so to speak. A dog is another vector of 1,000 numbers. But the question is, if you look at the interconcept space of vectors of 1,000 numbers that aren't the cat vector or the dog vector or the elephant vector, they're just other vectors that you can mathematically make.
Mm.
What is out there in the interconcept space? And the answer is, you can see it because the thing can make pictures of it.
Yeah. Yeah.
And what you see is bizarre. And what you realize is those things are things that we humans have not yet paid attention to.
Mm.
So one day, some corner of that might turn into a great fashion in art or something,
Yeah.
and people might all know what it is. But right now, it's just this weird thing floating in interconcept space.
Mm.
And so one of the things that's a little bit, so interconcept space is a place you can find sort of the doings of other minds. You can kind of the study I did of this, what I was interested in is kind of the mental images of alien minds. So you can take, for example, a trained neural net and that produces pictures of cats when you ask it to. And then you can change the neural net. You can make it an alien mind. And then you can ask it to make a picture of a cat. And the question is, what does it do? And the answer is it makes weird pictures. That as you make more and more changes to its mind, its notion of a cat, as it presents it to you, becomes more and more bizarrely different. And so in a sense, by seeing that, you are getting a sense of what an alien mind thinks a cat is.
So are they novel ideas, or are they just kind of hybrids of existing ideas kind of mulged together, or yeah, what are they? That's really
I
interesting.
don't know. I mean, I think that I mean they are a they're things we haven't seen before. And you could say, I mean, one of the things I realized recently is that, for our species, the sort of the biggest invention we've probably had as a species is language. And that's that allows us to do this thing of transferring concepts brain to brain and so on without, and so the question is, we got 100 billion neurons, we get language, the rats and mice have smaller brains, they don't have language in the same sense. Let's say we had a much bigger brain, what would we have that, is right now not a thing that we kind of, if you're a cat and you observe human language, we don't know what the cat thinks about human language, but we might at least imagine that given the idea of human language, a cat could appreciate the idea. Maybe not. I'm not sure. But the question is, what is out there that is beyond human language that we can at least have some idea of what it might be like? And so one of the
So
things I realized
I was just going to say, do
recently,
you think AI is going to help us with this then? Is AI going to eventually be able to deliver new branches of scientific research, new kind of scientific, methods and ideas?
well, it's easy to have new ideas. What's hard is to have new ideas that anybody cares about.
Mm,
In other words, if you study Ruliology, kind of the study of simple rules, it's very easy to generate, anybody, kids that we work with do this all the time. They make a cellular automaton rule nobody's ever seen before
mm,
because there's a big space out there in the computational universe. The question is, does the thing that cellular automaton does, is it something that one cares about? Does one say, wow, that's a great model for the growth of features of leaves on trees or something like this? Is it, or it's a great thing for making some effect for visual images or something like this?
mm,
That's really the issue. It's novelty is easy. The difficulty is novelty that connects to the kind of the kind of the tree of knowledge that we built up in our
mm,
civilization. So,
mm,
I think that what we see is the question of, and this question of, can we accelerate where we go with kind of sort of taking the ideas we have and sort of leveraging the go faster. That's kind of my life work, is about building the capability to do that.
mm,
Basically, what I've built in Mathematica and Wolfram language and Wolfram Alpha and so on, it's all about kind of giving one the ability to use sort of what is in principle possible in the computational universe, but giving one kind of the actual rocket pack to
mm.
actually fly around there,
Yeah.
as opposed to just observe what's out there. It's like,
Mm,
how do the humans get to fly around there?
mm. And
And
that's interesting because
that's
you said earlier a lot of your career has been about actually developing tools and tricks to make your life easier. The things like Mathematica, a lot of it has been about that. And there's something quite interesting that your theoretical thinking has been about doing. And perhaps
yes.
that's reflected in some way philosophically in things like the Ruliad, because it's a computational model. It has to be played forward to be able to reveal its true character, if you like. And that's
Yeah,
quite interesting.
one of the things that is a repeated embarrassment in my life is that, there are things I figure out and so on. And then a few decades later, I look back and I say, how did that happen? And then I realize there's like the starting to think about cellular automata and starting to think about kind of artificial physics. The fact that I did that was a consequence of the fact that I just spent several years designing a computer system
Mm,
where you're designing it from nothing. When you're doing physics or natural science, usually you think of yourself as reverse engineering from what is observed.
mm,
Whereas when you're building something in a sort of practical computer system, you're building from nothing to build up to something. And so that kind of conceptual difference from traditional natural science was kind of, as I realized a few decades later, was kind of critical to the fact that I ended up doing that. Now, the fact is my life has sort of consisted of an alternation between doing technology development and doing basic science, and now more of an interweaving of those kinds of things. And it is, yes, it's, if you look at the physics project, for example, that it is sort of a weird thing, because the fact that that project was possible was a consequence of a sequence of things built on top of each other that were each one was kind of a surprise that that piece got built. And in the end, you need a quite tall tower before you can do that project. I mean, you need a bunch of practical computational tools. You need a bunch of ideas about how computation works. You need to know a bunch of stuff about actual physics, et cetera, et cetera, et cetera. It's a very weird, I'm continually, even though that was now 5 years ago, I have this strange
How
feeling
did I
that
do
it's one of these,
that?
what's that? Yeah,
Yeah.
it was one of these things where, just the stars happened to line up in just the right
Mm,
way. And, many things could have gone a little bit differently. And basically the things that we managed to discover there, I don't think would have been discovered for 50 years, 100 years. I don't
mm,
know. It's one of these, occasionally one gets lucky, and there are these things that one can, sort of find that patch of reducibility, so to
mm.
speak, and jump ahead. And it's a and also in my life, the repeated story is once you see the story, it's sort of embarrassing you didn't see it earlier. Because once you've understood it clearly enough, it's kind of
It should have
obvious.
been, yeah, yeah, yeah. But maybe
But
do you think there was an intuitive sense of direction throughout this journey? Was there a sort of gut feeling that you were going to end up with a sort of because you mentioned the insight you had about the very early insight, the cover of that thermodynamics book, and you said
yeah,
that
right,
that gave you the idea that you can, physics isn't necessarily a fixed absolute thing. You can kind of move towards
right.
a foliation through some basic principles, and so yeah, that seems to have been the thread running through all of this in some sense.
I guess. I mean, I think that the you know, that fact about sort of what was exciting to me about that thermodynamics book, I only realized that decades later, that was what was exciting, so to speak. I mean,
Yeah, yeah,
I knew I was excited about it, but if you
but not
say
why.
why,
Yeah.
it's, it becomes clearer later on. And
Mm,
I think, I mean, I can say that the sort of, I mean, the main conceptual theme of basically every project I've done is take some complicated set of things out there, figure out what the underlying primitives that are the essence of that thing are, and then build up often some pretty elaborate engineering structure or scientific structure built on those fundamental principles. So it's kind of like I think that and I, you know, what is remarkable to me, for example, this recent work on biological evolution that I did, um, you know, I I almost had done that in the 1980s, but I didn't quite have the intuition that there will be that simple a model of what's going on in biological evolution. And you know, it is sort of shocking that even though I've had this experience of sort of the computational universe and what happens out there, um, it's still it's very hard to really live that intuition. I mean, you keep on thinking, well, this system is too simple; it won't be able to do this or that thing. And I
yeah,
have
does
this
it?
statement for people I'm working with. It's like the computational animals are always smarter than we are, so to speak. They always manage to find a way to do these weird things that we never
Mm,
anticipated. And that's
mm,
what is interesting to me is that
mm,
if I'm looking at sort of the things I try to do, I suppose the other thing that's pretty helpful at this point is at some level, I like figuring stuff out, but I don't have, it's kind of like the chips fall where they fall. I'm more interested in where the chips fall than I am in saying, I've got this thing that I'm trying to get to. let me prove
Mm,
that thing. And if you want to do science, that sort of valid science, so to speak, it's actually, I'm increasingly realizing how useful it is to kind of not have an emotional investment in where the chips fall.
mm,
And it's a thing where and it's hard to do that because
mm,
you have to have some hypothesis when you go into a project, otherwise you don't go into the project.
mm,
And but then once you're in there, it's kind of like you've got to be able to kind of be sufficiently detached from things that and when people say, do you think you found the fundamental theory of physics? It's like, look, it's there's some implication that there's sort of a competitive aspect to it's your theory instead of somebody else's theory
mm.
type thing.
But it's just
And
where the dice landed, the kind of thing.
yeah, I
Yeah,
mean,
yeah.
to me, it's like it's I mean, it's it's something where I'm like, it's really interesting what comes out, and
Mm,
what's it's sort of really remarkable that it landed in this place, and it's kind of uh, and also I feel, I mean, it's sort of always interesting to me because I kind of watch the science that I do, and it's kind of like, did I get it right? Did I not get it right? I've, I tend to have the experience that once I'm pretty sure I know what I'm talking about, I actually know what I'm talking about. And
mm.
that, there'll be long periods of time where I know I don't know what I'm talking about. Um, but
So when you're
and so
prepared to
that's
come forward, you generally do know what you're talking about. But by the time you're
right.
prepared to come forward, yeah, yeah,
Right.
that's
Well,
fascinating. Yeah.
I mean, I tend to do things in a very open kind of way. So
Mhm.
I'll live stream the moments when I don't know when I know I don't know what I'm talking about.
Mm,
But it's kind of and so, for example, with this kind of questions about physics, it's
mm,
like, this cannot possibly be wrong. This is the way it is. And that's, and it will be a while before other people
mm,
kind of, before it's sort of funny because, like, the concept of computational irreducibility, for example, or the concept that you can think about the universe computationally. These are concepts from the 1980s where like computational irreducibility. At first, I didn't know if it was true. I eventually kind of developed a fair amount of intuition around it, a fair amount of evidence, and so on. But now there's a generation of young scientists
mm,
for whom computational irreducibility is obvious. It's kind of axiomatically obvious. Um, and it's kind of, you know, it's a challenge for people who invent ideas for them to become axiomatically obvious,
mm,
because that's kind of what you need to be able to build the next layer of ideas, is that layer of ideas has to be obvious. If you keep on kind of worrying about whether, wait a minute, those foundations might not be the way I think they are, let me worry about that, you never get to build the next stages on top of that. But I've been, I suppose, it's been a fortunate coincidence, I suppose, that I've, you know, the process of developing technology that is itself necessarily about getting to the essence of things, because
mm,
that's what it means to kind of build a kind of computational notation for things in the world,
mm,
is you have to know what are the essential elements to put into that. And
mm.
that's, it is very convenient that my day job is deeply aligned with kind of the intellectual sort of thrust of things that I'm interested in for for purposes of basic science and basic thinking and so on.
Mm. Just a bit of a mad idea on this, actually. If you had enough computational power and you could run your kind of physics project on a super duper computer, could you have sort of simulated minds emerging within that um,
I think
foliation, if you
so.
like? You think
It's
so?
actually an upcoming project has to do with looking at exactly that. So
Really? Oh my God. That's
so
very
good
interesting.
suggestion. Yeah. So I think that uh now that we have some characterization of what observers are like, we
Mm,
have the possibility of asking, do they emerge, sort of, what is the process through which they emerge?
mm.
And I don't yet understand this very well, but
So you think they did
I,
emerge? Yeah, the observers weren't there, haven't always been there. They are an
well,
emergent
observers like
phenomenon.
us weren't always there.
Right, right, right. Yes.
I mean,
Yeah.
but I don't know exactly what matters for observers like us. For example, it could be that self-replication, which you might think of as being some very detailed biological thing, it could be that self-replication really matters for observers like us. And here's why. Because if there was just one mind in the universe, the kinds of things that we sort of deal with as minds, like concepts that we can exchange with other minds, wouldn't be there. If there was just one, if I was the only thing in the universe, so to speak, that was an observer like me, it wouldn't be, my existence would be very different from the existence that I have, from the fact that I can have a concept that I can package up and bounce off another mind and so on.
There probably
And
couldn't be
so,
any language without other minds, could there?
well, yeah, that's right. Well, it could be the case, but then you're back in the same situation of, it could be the case that within a mind, the question is there anything packageable that emerges within a mind that is not just, oh, it's a random collection of neuron firings? But that's this question of, is there sort of an intermediate language of neuroscience? Are there packaged concept-like things that emerge within a mind? Well, as soon as there are, it's as if there are multiple pieces to that mind, and it's sort of as if there are multiple minds. So, you could say within human society, are there, where there are many distinct minds, but human society kind of has a mind as well. And you can ask, how does that, the fact that you can identify these separate minds is kind of the story of many identical pieces. And so I'm wondering whether self-replication, which I've always assumed was kind of a detail of biology, I wondered if that's actually more important in the existence of observers like us than I had imagined, because it kind of is the thing that lets you kind of have many sort of similar things that can exchange concepts and so on. So, I think we don't yet know. Hopefully we'll know in a few months, maybe, if a little bit more about kind of what aspects of, where, of all the things that happen in the Ruliad, being able to point to where is there the emergence of observers like us. And then a question that we'd like to ask is, okay, how frequent are observers like us? What's the density in Rulial space of extraterrestrial intelligence, so to speak? Or, I don't know what the right term for extraterrestrial, I suppose it's I don't know, beyond human.
Otherworldly. Yeah.
Right. I mean, it's kind of, so and then it will be lovely to be able to know something about kind of, as we go a certain Rulial distance away from us in the Ruliad, how different are those minds? How difficult is the translation? So, to go from one place in physical space to another, you make a rocket, you zoom off by spending a bunch of energy to move to a different place. If you want to move in Rulial space, you are doing a translation from one kind of computational representation of the world to another computational representation of the world. And that takes effort as well. And the question is to characterize that effort. By the way, the characterization of that effort is something that's never been done. So if you ask, between different computer languages, between different human languages and so on, what is the, what's the sort of distance between these representations of reality, so to speak, or representations of ideas? And we don't have any such metric. One day there will be such a metric. It will be something a bit like information theory, and it will be sort of obvious in retrospect how that all works. And
so we could compute the similarity between different theoretical models and things like that.
Yeah, right.
Right.
And
Okay.
being able to ask the question, we'll be able to say the dolphins are this distance away in Rulial space, the mosquitoes are this distance away. Being able to quantify that type of thing. And I think, so, there are a lot of these, I think there's some sort of big questions which may actually relate more to observers than I expect. For example, there are questions about biology. How important is it to us that we're biological? And, we kind of imagine that many aspects of us, and it's certainly true, are replicable in digital systems, but and ultimately that has to be true because it's all sort of computational in the end. But the question is, observers like us, does it matter that we're made of a few kilomoles of atoms, and does it matter that we have 100 billion neurons and so on? And I think one of the things I've been interested in recently is kind of the foundations of biology, and in that area, there's not much theory that's known in biology. I mean, a lot of what we say about biology is, well, it just happens to be that way. A little bit like what I'm saying about what's happening in machine learning.
Mm.
It just happens to have learnt that thing. And if we ask, why does the Stegosaurus, why do Stegosauruses exist? The stories become very, well, given that we were going to have a Stegosaurus, it's going to be like this because it, eats
Mm.
this kind of thing or whatever. But
Yeah.
why did it exist in the first place? Well, we're not really quite sure. But I think
Mm.
the the um, the question um, of what let's see, I lost my train of thought here. I'm distracted because I have to go fairly soon here. But we're talking about biology, and we're talking about
Mm.
kind of the theory of biology and the idea of, you know, is a Stegosaurus theoretically predictable?
Mm.
And what is predictable, what's not? Well, I think one of the things in biology, there are basically two big theories in biology. One is natural selection, and the other is that the genome is
Mm.
ultimately digital. Those are two sort of big theories.
Mm.
And the rest is sort of, oh, and it's all chemistry type thing. I have a feeling that one of the things that we've sort of meta learnt from molecular biology is that it isn't really chemistry. There
Mm.
are really, molecules don't just randomly bounce around most of the time. There's a high degree of orchestration in what the molecules do.
Yeah.
And, uh,
There's a
it's
downward
similar.
propagation through the scales, isn't there?
Maybe, maybe. I mean, I don't know. I mean, the question of what you might say that about this biological evolution study that I did, that the overall fitness determines what's happening at a small scale, but that determination, it's very free will like. It doesn't really have
Mm.
you can't trace the sort of deterministic, okay, we had this fitness, so we'll
Mm.
have this or that thing happening at a
Yeah.
smaller
And,
scale.
and Stephen, very briefly, this reminds me of some of Mike Levin's work where they've demonstrated that the behavior of cells can be quite plastic. So they've got these frog skin cells that are doing weird and wonderful things. They're cooperating, they form these new entities called xenobots. They've never existed before. So highlighting the plasticity of biology at that lower scale. I mean, it's fascinating stuff. That they're self-organizing. They seem to display volition. They seem to
One
have
of
a.
these days I should have a chat with Mike
You
Levin.
should talk to
I think
Mike.
he,
Yeah.
yes, right. Multiple people have said that. I have a slow rate of getting around to actually having these conversations, and
Mm.
and occasionally people say you should have this conversation, and I have it, and it's terrible.
Mm. Yeah, because I mean,
But usually,
they're finding agency and cognition in the most basic systems. These sorting algorithms that seem to display delayed gratification, and it seems to tie into some of the things you've talked about. So there may well be some
right. Well, I think
healthy
that
convergence.
right,
Mm.
the principle of computational equivalence, you know, shows up in all kinds of places, and
Mm.
you know, it these things don't surprise me. I'm always, one of the things that's always challenging is computer experiments are hard enough, at least to interpret. They're easy to do. They're easy to run again, and they always do the same thing, and that's straightforward. When it comes to actual experiments in the world, you know, these always have, they're always fraught with all kinds of, what's really going on, what, how do I understand,
Mm.
did the rat really understand that, or did the rat just do that because
It,
because on that, it's like the horse that could do arithmetic, for example, the
mm.
horse called Hans that could do arithmetic,
Mm.
which, in the end turned out to be actually, I was looking at an animal cognition study recently, and I was pointing out to the person who'd done it that they have this whole list of the different cognitive levels of different animals, and the horse is particularly low. And I was like, is that the legacy of Hans? Because people got so embarrassed about, horses, about it being kind of a fake to have
Mm.
the horse do arithmetic because there was just a cue from its owner, so to speak, that horses
Yeah.
got downgraded in the ranking of animal cognition. But those experiments are really hard. That's
Mm.
that's so it's always uh, I'm it's always challenging to get experiments to the point where, to my mind, I mean, with computer experiments, getting them clean enough that they're interpretable is hard. With physical experiments, getting them clean enough to be sure that they're actually right and that wasn't some, effect that wasn't what you thought it was type thing. It's always very hard. And I'm always a kind of one of my principles about experiments is if I'm ever going to use some result of some experiment, I want to see the experiment. Don't just read a paper that somebody wrote.
You want to do it. It's almost want to do it.
Yeah,
yeah.
Doing it is even better.
Yeah.
But that's usually out of range. Although there's a company that for the last decade has been building an automated lab system based on our technology stack, and so lots of pharma companies and things like that now use their automated lab. But I've been getting ready to do my first actual adult chemistry and biology experiments, although it's a bit daunting because you have all these different kinds of instruments and they have an infinite number of different parameters. And for anybody in the biz, they know, oh yes, you use temperature such and such for the first stage of a PCR experiment or something. But it's, if you're not in the biz, those are not things you immediately know, just as I would know for computer experiments. Oh, well, like many, many times, I'll sort of try some choice of parameters at first, because I think that's where something interesting will be. And, and it turns out it is there. But, how would one know that if one wasn't kind of experienced at doing these things?
Indeed. But, well, I think we're probably close to the end there, Stephen. Thank you very much for talking to us. It's been a massive pleasure. And tons of homework and reading to do after that. So thank you for that. And yeah, it's been brilliant having you.
Thanks.